by Anna Karlin on avoiding cascading failures for time of use pricing.
Okay, so, ooh, it's loud. So this is joint work with Shuchi Chawla, who's right here, Nikhil Devanur, who I thought would show up but didn't, although he now has a beard, Ander Holroyd, James Martin, and Balu Sivan. Okay, so the motivation for this work comes from commodities of a temporal nature, like cloud computing and energy, basically situations where supply and demand fluctuate over time. You might have good stochastic models for what that supply and demand is going to look like over time. And the arriving jobs are basically interested in getting service within a window of time. And what we're looking at is the idea of using pricing on a per time unit basis in order to balance supply and demand and expectation. So this is what we're calling time of use pricing. And since we're only balancing supply and demand and expectation, there's a question of how well will such a system work under the natural stochastic fluctuations that happen. So that's kind of the goal of the work, to understand that. So the work is within what some of you are familiar with as the profit inequality setting. So we're looking at a situation where resources are priced in advance based on stochastic information about job demand. I'm assuming fixed supply in this talk and only demand is stochastic. So jobs will then arrive in any order and take their favorite resource given the prices. So a job will have a value and it will be only interested in, it has a window of time of interest. It's only interested in resources that are priced below its value. It's always going to want to take the cheapest such resource that it can. And the goal is to price those to maximize the value of allocation. And the benchmark is the expected value of the optimal offline allocation. So this is the allocation you would get if you knew exactly ahead of time which jobs would arrive, and you could assign them optimally to maximize expected value. So let's just warm up with a very simple example that many of you have seen before. Suppose I just have one resource and my stochastic model is two possible jobs. Job 1, which is certain to arrive and has value 1. Job 2, which has very high value, 1 over epsilon, but is very unlikely to arrive. Okay. So the claim is that no matter how I price in this setting, my expected value is going to be 1, whereas opt is going to be 2 minus epsilon. This is the example Matt gave. So the problem is that, if I price above 1, then only this job will be interested. If I price at or below 1, then this job will arrive first, will grab the resource. And so the online algorithm doesn't really have a choice because they arrive in this bad order, low value to high value. Whereas the offline can, assign to this one if it arrives, and if it doesn't arrive, which has probability 1 minus epsilon, then it gets this one. And this kind of result has been, so that was a factor of 2 kind of competitive ratio sort of situation. And this has been extended to much more complex settings, like, for example, the work of Feldman, Gravier, and Luchier shows how to solve this kind of problem when the buyers are, if you have a set of heterogeneous items, the buyers are interested in, only one item. Each buyer has a value for each item. They're going to come in some adversarial order, and based on the prices, each buyer will choose their favorite item given what's left over. And basically, what they show is given priors, there's a way to set prices so that the expected value of the allocation is half of the expected value of optimum. But what we're interested in this talk is approximations that get expected value as, very, very close to 1, okay? So, and that's impossible even in the example I gave on the first slide. You can't do better than 1/2, a factor of 2, with the example I gave before. So a way to get around that is to use extra capacity. So let's do another very simple example. Suppose that I have B identical resources. So this is sort of, imagine these are the resources that are available at time t only, okay? And I have many jobs demanding 1 unit of resource, each with a low probability of arrival. So the claim is that if B is large enough, then I can price so that I get, basically a lot of a very large fraction of the social welfare. So here's kind of the picture, and it'll be useful for understanding later. The model for the jobs is that each job has a value. I've sorted them from high to low. And each job has a certain probability of arrival, okay? So these are the QIs. And so what I want to do is set a price. If I set a price at some value, okay, then only jobs that show up with value above that are going to try to take the resource, or one of the resources that we have. And the simple observation is that if I basically take sort of the high range of the values such that the expected number of arriving jobs is 1 minus epsilon times the number of resources I have. So if I do that, then that guarantees that the expected value of those resources is at least 1 minus epsilon times the expected value of opt. Okay. Then even if they arrive in the order low to high, each one of them is very likely to be served because, we're very unlikely to have more arrivals than the capacity under this assumption that B is basically what you need to get the turnoff bound to work. Okay. So epsilon to the minus 2 times log 1 over epsilon. Okay, so that's a very simple case where once we add some extra resources, then we can do very, very well. So here's the problem we're going to discuss today. It's a generalization of that problem. Now think of time as going left to right here. And I have a certain capacity at every time slot. So I have a certain number of resources at each time, okay? And here's the stochastic model of job arrival. It's similar to what we had before. So every potential job has a value and a probability of arrival. But now the jobs also have a window of time, okay? And what that means is that they're happy to receive a resource at any slot in this window, okay? So just to observe now, if every window was of size 1, this would just be a bunch of independent versions of the problem I just talked about, okay? So the question we're interested in is, can we set prices so that, price the time units, so that if jobs arrive online in an adversarial order and upon arrival each job grabs their favorite available resource given the prices, that we'll still get this 1 minus epsilon fraction of the expected value of opt, okay? So the easy part of this problem is the pricing, just like what we did in that simple example. So what you can do is you can formulate and solve a so-called expected linear program that optimizes for the value of the allocation. That gives an upper bound on the expected value of the optimal offline solution. You can read the prices off of the dual. Complementary slackness conditions will guarantee that every job that would be accepted by the LP optimum is assigned to one of the lowest price slots in its window, which is happy for the jobs. So the hard part of this problem is, so basically this is a standard approach that many people have used in many settings, and what that guarantees is that essentially the expected number of arrivals to any slot in our window, which is the lowest price slot for each job in its window, is kind of 1 minus epsilon times the capacity at that point in time. The problem with the understanding to prove that this works very well is understanding the interaction between slots at different times. So if a job's, we will occasionally have overflow, just 1 second, we will occasionally have overflow, and if a job's assigned time slot, the cheapest price slot in its window is not available, an arriving job, then it may grab slots at other times, and we're worried about the potential for cascading bad events. Yeah?
So what information do you have at time 0?
I have all that stochastic information at time 0. So this is obviously, okay, that's an assumption here. Sorry, not this. Basically, I know this entire distribution, which is like a list of jobs, each with a value, a probability of arrival, and a window.
Oh, probability of, okay.
Yeah. So, yeah.
So you know the window, but you don't know whether the job is going to arrive or not.
Yeah, I don't know whether the job is going to arrive at all. And also, just to emphasize, we want this to work no matter what order they arrive or no matter what order they grab slots and stuff like that. Yeah.
And are you allowed to vary the prices online after some jobs have arrived?
No, we're not going to. Well, theoretically, you would be allowed to do that, but we're not going to be doing that. Okay. So, okay. So So let me first make sure you kind of understand what the process will be once we've set the prices. Once we've set the prices, each job will toss its coin as to whether or not to show up with its associated probability. And it will start, exploring, trying to get a resource within its window. So for example, this job here, which has values. So I've already set some prices here. They're the numbers inside. Let's say job 3 here actually shows up. So it's first going to try to grab a resource of price 1, okay? And then if that resource is not available, it'll try the resource of price 2. And if that resource is not available, try the resource of price 5. And if all 3 of those are not available, then it's going to give up because 8 is too expensive for it, okay? Its value is below 8, yeah?
So when does the job decide to use one of the resources at the time that it arrives, or?
Anytime it wants, anytime it wants. So we are assuming nothing about timing of different events, nothing, okay? It's just, so that's the point. You don't know what will be taken at the time. This job could actually theoretically show up at this time and grab a slot then. It could do whatever it wants.
So I can think of it as like intervals are adding to the picture one by one.
Yeah, but we're not going to make any assumptions about the order. Okay. The only assumption about this job is that it only wants a resource in this interval. That's all. Okay. Okay, so I described this sort of hopping process of a job that, it tries to find a resource here, then it tries to find a resource here, then it tries to find a resource here. So that induces a directed graph, okay, on these time slots, okay? So for example, we have an external arrival coming in here, and then, the job could potentially hop from here to here and then from here to here, okay? If there was a job with this window, then there would be an edge from 1 to 8. If there was a job with just this window, there'd be edge from 1 to 5, and so on. If you have jobs, if you have slots with the same value, you could potentially have edges in both directions. Yeah.
So I missed, what do you have information about the distribution of the demand at any time?
We have up front this entire, everything that's depicted here, we have up front. The value, the window, and the probability of arrival for each job. I have a list of all that for every single job.
Set or distributed?
This is the distribution. It either arrives or it doesn't with this probability.
Thanks.
But the window is fixed.
The window is fixed, yes.
But then the window might be inactive, right? That's
the window might be inactive, yes. Good, okay. All right, I think you understand the problem. Okay, so we have an induced graph here. And basically, the main part, we're going to show that this pricing in this way works very well, and that we basically need to show that cascading bad events don't occur. Okay? So let's start with a couple simple examples. So a very easy example would be if basically the directed graph, this hopping process, just looked like, you arrive at time t, then you try t plus 1, t plus 2, and so on, okay? In that case, I could just, and we already have the pricing that guarantees that the expected number of external arrivals is at most 1 minus epsilon times the capacity at time t with exponential tails. So basically, we can just start at the beginning and do a simple inductive argument to show that the number of forwards it's very unlikely that there are any forwards, and then there's also an exponential tail, and so when you combine that with the arrivals, you're very unlikely to have more forwards, and so on. Okay.
Just to be sure, this is the case that the jobs arrive from left to right?
I don't even care when they arrive. It doesn't actually matter when they arrive. The point is that no matter when they arrive, okay, the total, if I look at time 1, there are no forwards to time 1, right? So I'm going to worry about the possibility that there are forwards to time 2. The worst case for a job arriving at time 2 is if it comes in after those forwards have occurred, right? So yeah, it is essentially left to right. That's kind of the worst case here. Okay. And yes, I should have said that right. Okay. And similarly, suppose that the forwarding graph looked like a directed tree, okay? Then again, where the in degree at every node was constant, Okay. Then again, a simple inductive argument from the leaves up shows that every arriving job has very high probability of service. Okay. So this is again, so here we're using the independence of the forwards from the different subtrees, and yeah, that's basically what we're using. And the fact that the worst case is if they arrive in this order and then they keep percolating up as long as they can. Okay. As long as they need to, yeah.
Did I miss? Did you say what happens if the capacity is 1? Or did I miss?
Yeah, we said that you can't do better than a factor of 1/2.
But you can get to 1/2 in this case.
You can in this case. That actually was done essentially by the Feldman et al. Work and other works and so on, yeah.
So what I don't understand is if the sum of all, the number of jobs total was larger than the sum of all capacities, then that clearly wouldn't hold true, right? Like you would
So
have,
we've set, okay, we in advance we set prices so that the expected number of external arrivals at every node, which a node here corresponds to a time slot, is less than the capacity at that node. So the overall expectation is below, the expected demand is below the supply at every single node.
so when you say the arriving jobs, you're referring to the arriving jobs that are willing to pay.
Yes, but all the other jobs have already been like tossed out the window. Okay. Yeah.
So if the job arrives on time t, it knows what the price will be on time.
Yes, all the prices are set in advance. So the jobs, so this is one of the nice things about that I'll just mention right now, is that from the perspective of the jobs, this is completely truthful. You know, we're not, you know, everything is just great for them. They get to choose their favorite slot. It's all good from that perspective. Okay. So the problem, though, is when the graph has cycles and multiple paths that meet at the same node. Then the kind of simple inductive arguments don't work, okay? Because the forwards to node 3 depend on what's happening at node 2. The forwards to node 2 depend on what's happening at node 3. Even if there were no cycles, the fact that you have multiple paths coming from the same node means that the arrivals here are not independent of each other, okay? So that's kind of the issue we need to deal with. But we can deal with that. And so the theorem basically says that, as long as we have basically the number of slots at each node that corresponded to the single slot case and a set of prices that guaranteed, I'm doing informal here, the set of prices that guaranteed the expected demand isn't too high and a directed forwarding graph with constant maximum in degree, then even if the jobs arrive online in adversarial order or forward adversarial, blah, blah, blah. Okay. So I just want to say that this theorem doesn't have anything to do with the prices anymore. It's just the prices were there to guarantee that the expected external arrival rate was correct. But the theorem applies even in kind of an abstract setting like this. Okay. So I'm going to try to give you the idea of the proof. So the high-level idea is to actually show that the worst-case load is when the induced graph kind of looks like a tree. And so let me try to give you the idea here. So for the rest of the discussion, let's fix a particular node, say time t, and we want to bound the probability of overload at node t. So the probability that an external job, just one second, arriving at that node doesn't find a free resource at the very first node it shows up at. Yeah, Bobby?
When you covered the tree case a couple slides ago, you said there was a restriction the tree has bounded degree. Now that you're pinning the entire proof on the graph being a tree.
Well, my directed forwarding graph has constant has bounded in degree.
Okay, great.
Actually, you can add a log d here and handle higher degree. But anyway, that's okay. So we're going to argue that with high probability, with probability 1 minus epsilon, every single job that arrives is happily served at the very first node it shows up at. So the first part is just to argue that for any fixed set of arrivals, so for example, here I have 3 arrivals at this node and 3 arrivals at this node, 1 here and 0 here. For any fixed set of arrivals, if I want to look at the load at node 1. And what I call the load at node 1 is the number of forwards. By the way, these arrows here represent a job searching for a resource. So this blue job didn't find a resource here, so it tries here, and then it tries here. Okay, that's kind of what this picture represents. So the first claim is that for this fixed set of arrivals, and my goal is to bound the probability of a problem occurring at this node, I can reroute these paths the jobs take so that they go along a tree, induced tree here, without reducing the load here. So just as a simple example, if I just simply reroute this blue path so that it goes up here, then when I ignore the parallelism here, I have a tree, okay? So that's something that you can do for any fixed set of arrivals, a fixed node we're trying to bound, and there's going to be some tree you can reroute on that will maintain the load at the node you're trying to bound for that particular set of arrivals. Okay, so I'm going to state this a little bit formally, but so here's the notation. I have the load, the forwards on arrivals on node 1, given the arrivals, and so given a specific set of arrivals, like 0 at node 1, 1 at node 2, and so on, and a specific set of paths that the jobs take. And I said that we could reroute along some tree. So there are many trees that in this graph rooted at node 1. Here are 4 of them. Okay, I'm going to call that set T of 1. And I'm also going to call L1 sup T, the load at node 1, if all the forwards were to only go along this tree. So suppose that whatever jobs arrive, if I'm using this tree, they always go like this. That's how they try to find a resource. Okay? So the claim is, and this is not too hard, I'm not going to show any details other than that example I just showed, is that for a fixed set of arrivals, basically if node 1 in my picture was overloaded, then there's some tree such that if I route on that tree, it's still overloaded. Okay? Yeah.
You cannot reroute arbitrarily, right? So you have intervals. So
those are gone. Okay. The intervals are gone, and what we have left was that forwarding graph. And I'm going to allow the jobs to take any path they want whatsoever in that forwarding graph. Now, the reality is they would only take paths that correspond to their interval. But I'm now, this is why I was trying to say that we've moved away from that particular setting to a more abstract setting where I simply have a graph. I have a right number of external arrivals.
Want to analyze the worst case. So
this worst case, so yeah. Yeah, exactly. So the point is that it suffices for us to bound the probability that there's some tree at which node 1 is overloaded. Now I have changed the little a, which is a fixed set of arrivals, to a big A, which is the random variable number of arrivals, okay? Set of arrivals at different nodes. Okay, so we want to bound this. And basically what we want to say is what's the probability that if all if I look at the worst case over all my trees of the load at node 1 for the arrivals that it's overloaded, the worst case over these trees. And so it's complicated to think about multiple trees. What I want to do is combine these trees into a so-called tree of trees. And before I do that, let me just observe that I've changed the names of the nodes to reflect the path that the packet takes in this tree. So here, the packet would go from 4 to 2 to 1, so I've named that node 421. And similarly here, it goes from 2 to 1, so I've named that node 21. The reason that we've done that is to make the following picture clear. I hope that you can see. I almost told me last night to make this bigger, but I didn't. So the point is that what I can do is I can combine all these trees into this so-called tree of trees. What is this tree of trees? It represents directed paths, simple paths towards towards node 1. All of the nodes at level 2 correspond to 1-hop paths. Nodes of level 3 correspond to 2-hop paths, where you have an edge from a node to another node if, after you take the first edge in this path, that's the rest of the path, okay? So the point is that the color scheme is intended to show that all of these trees, by construction, are embedded in the tree of trees, okay?
It will be exponential size.
Actually, it could be exponential size. Yeah, could in fact very much be exponential size. But the integree at every node is constant if the graph had constant integree. Okay, so we're actually not going to care about that. Okay, so here's the thing. The claim now is that if I let my arrivals show up. So here there are arrivals A4. Here there are arrivals A4, A4, A2, A3, and so on. Okay, I have my random arrivals, and I want to argue. The claim is that if the maximum of one of if the routing according to one of these trees would result in overload, then routing on the tree of trees will result in overload, because in particular it contains all of those trees happening simultaneously. I hope that pictorially makes sense. It's a little confusing. So basically what we claim is if I call T1 this tree of trees, then the probability that the node 1 is overloaded in the tree of trees is greater than or equal to the probability that the maximum tree is overloaded. Okay? So the problem is I can't use the analysis for trees that we had before, because we no longer have independent arrivals at the different nodes. Okay? So the beautiful thing is that you're going to be I'm just going to do this fast. You're basically going to be able to replace these random arrivals by independent draws from the same distribution. And the claim is that that's only going to make things worse. That the probability that the root is overloaded when I have an independent arrival of the correct type at each node is greater than or equal to the probability in the original tree. Okay? And once we've proved this, then we can apply our analysis for trees to upper bound things, and it's good. Okay, so the key lemma, I just want to show you this because I think it's very cute. That certainly had nothing to do with coming up with it. But it's like so cute and so simple and so useful. I just have to show you. So suppose you have two functions that are non-decreasing, and x and y are IID real valued random variables. Then the claim is that the maximum of g of x and h of y, where these are independent instantiations of the same random variable, stochastically dominates the maximum of g of x and h of x, where we have x, that's the same random variable x. And this is actually two-line proof. Let's fix some particular a. The probability that the maximum when I take independent random variables is just the product of the probabilities. Whereas the probability that the maximum is less than or equal to a when they're the same random variable is, in fact, just the minimum of the two probabilities. Actually, I drew a picture here that I was too lazy to put in the slides. So here we have our function f of x, we have our function g of x, and we have the values x might take. And I fix a particular a. So the probability that g of x is less than or equal to a is just the probability that capital X is below x1. The probability f of x is less than or equal to a is just the probability that capital X is below x2. But if I need the max to be less than or equal to a, then basically I need just the minimum of basically I need to look just at the minimum of those. I don't know if that wasn't clear. It's very simple. You'll look at this later and you'll understand. So the point is, what this shows is here we have the product of two numbers less than or equal to 1. Here we have the minimum of two numbers less than or equal to 1. Obviously, the product is less than or equal to the minimum. So that gives us this, that this holds for any a, which means the probability that the independent version is above a is greater than or equal to the probability that with the same random variable is above a. So I just love that. Okay, so bottom line is we get that theorem, and we can use it to get the cloud result. And I just want to make a note that there's more work involved in that, because the forwarding graph in the cloud setting does not have bounded in degree, and yet we're still going to be able to get the same bound we had for a single slot. But there's some reduction you can do that involves shortcutting forwarding paths that I can't get into. And we also have an extension of the theorem to the case where jobs want more than one slot, like a contiguous sequence, but then the capacity at every node needs to be much bigger. Just a quick comment on related work, which I didn't mention mostly yet. So there's an extensive literature on worst case type results in this setting, of this cloud setting, okay? And this so I just want to, to compare. Of course, they're worst case, so that's nice to have that very, very strong assumption, very strong guarantee. but they're generally not prompt in the sense that you don't know your payments right away, even when you arrive right away. Competitive ratios can be large, and they're generally not truthful with respect to all parameters without some additional assumptions, and not as simple. So here this was just very simple. We priced everything in advance, and we let the jobs do what they wanted to do. Okay. And then there's stochastic. There's work on online matching that's not truthful. There's some relationship to queuing literature that is complicated that I don't understand. And ask Nikhil. And okay, so that's it. So the nice thing is we have essentially no loss relative to the single time unit setting in terms of the capacity needed. And that's it. Thank you. Oh.
So if you had a general bipartite graph, does this thing work, or does it measure intervals?
Yeah, so I think that, well, the problem is that this graph, the resulting graph would have very high in degree potentially and be very, very complicated. So, I mean, you could use enough resources to make it work, but I think it would be not interesting.